So after doing Stokes theorem and solving some examples explaining the orientation, I want in this short video to explain the relation between Stokes and the Green's theorems. Yes, there is a relation between the two theorems. Let's see what kind of relations. Now let's remember what was Green's theorem. Green's theorem was about if C is a closed curve in R2, right? Then the curve integral f dot n dA, f dot dr is the double integral over d df2 by dx minus df1 by dy dA. Remember, so this is exactly what we have. So you have a closed curve C. You have the orientation. You have the orientation this way. Remember what was the meaning of D? D is the interior of your curve, like this. Now remember, all of this is somewhere in R2. Okay. Now we want to connect the Green's theorem with Stokes theorem. And let me say something. Why do we expect to have a relation between Green's theorem and the Stokes theorem? Let's remember, path independence, I'm just talking about some stuff collected from everything we've done so far in this chapter. So kind of we are connecting things together, kind of. Remember, what was the meaning of a function being conservative? Conservative, it meant that the derivative of f2 with respect to x is equal to the derivative of n with respect to y, right? But this is true only for functions that are from R2 to R2 in two components only. But then we said, okay, if the function was f1, f2, f3, so if it's a function from R3 to R3 with three components, three variables, then what was the condition? Remember, it was about the curl is equal to 0, and the curl is equal to 0, if we recall things together, it meant this thing, it meant that the derivative of f1 with respect to y is equal to the derivative of f2 with respect to x. The derivative of f1 with respect to z is 3 with respect to x, 2 with respect to z, 3 with respect to y. Remember, this is the meaning of a conservative function. So somehow now, if we look at these things, somehow, okay, I'm not saying this is like a very clear relation, but when we look at conservative functions, we see this quantity, okay? Now, if we look at this quantity, this is exactly what we're seeing inside the integral in Green's theorem. Now, what about the other quantity, this thing? This is exactly what we see inside what? The surface integral in Stokes theorem. So from this, so the two quantities here are related as descriptions of conservative functions. So this is why we expect to have a relation between Stokes theorem and Green's theorem. Okay, so this is Green's theorem. Then what about Stokes theorem? Stokes theorem was, if you have a surface and so on, we have the curve integral f to dr equals the surface integral of the curl. This is the curl, right? So just to remind you, if you have a surface in R3, now I'm doing things in R3, okay? So these are the axes somewhere. I'm drawing a surface in a strange way. It is a surface, right? This is a surface. It is. Okay. Now this surface has an opening curve. This is the opening curve. It has a certain orientation. Now with this orientation, if you agree, my normal vector has to be somehow like this. This is the upward normal vector. So again, in Stokes theorem, what distinguishes the orientation is if you imagine yourself as the normal vector, looking down at the curve has to be oriented counterclockwise. This is exactly my situation. Okay. So this is Stokes theorem. That was Green's theorem. Now, what is the relation between the two stuff? If you want to connect the two quantities, then let's look. So now what I'm taking is, let's see, be a closed curve in R2. Okay, so this is R2. You have a certain closed curve, whatever. Okay. If you agree, you can view this curve in R3. How is that? If you draw the axes in R3, this curve, you can draw it. This is the x-axis, the y-axis, the z-axis. You can draw exactly the same curve down on the xy plane, right? Like this. This is my curve. Okay? Okay. Then, if you look at the interior, this is the interior of the curve. This is the interior of the curve. Now, if you do this shaded area, okay, it is the interior of the curve, but I don't want to look at it as the interior of the curve. Now, I want to look at this thing as one entity. The curve, together with its interior, it becomes a surface. This surface is an open surface. What is the opening curve? This is the opening curve C. So I can apply Stokes theorem in this scenario. So I want to apply Stokes theorem on this surface. This is the idea. Okay, so we started with the curve in R2. And now we are saying, look at it as a subset of R3, apply Stokes theorem. Okay, so this is what we've done in the previous page. So you have a curve somewhere like this. This curve is C. It has an interior. Sorry, I had to change the application I use because the Apple application keeps struggling. It keeps quitting from the application. So I had to use this. Let's see what happens with this application. Okay, so now what are we doing? So now let us be the surface and the x, y plane with boundary curve C as shown. Okay, as shown. Now I have two things. So Stokes theorem says that the curve integral of f dot and dA is equal to the surface integral of what? Of the curve, right? Okay. Now in this case, we're dealing, please remember, I'm dealing with things, everything is in R2. Everything is, or let me say was in R2, but I'm shifting everything to R3 as a subset of R3. So even my function, this is very important, even my function is a function in R2. It's a function that maps R2 to R2. It has only two components. It doesn't have a third component. It doesn't have a z. For example, the first component is xy, the second component is y squared, anything. We don't have a z, remember this. But now I'm somehow looking at this function as a function acting as a function now. I want to look at it this way. I want to look at it as a function acting on this region. So if you agree, it's still acting f1, f2, and the third component is 0. It doesn't have any value, any third value. It is affected only by x and y. And this f1, this f2, they only depend on x and y. This is very important, okay? And sorry, I did this mistake again. This is not f dot n. This is f dot dr, okay? Okay. So this is our Stokes theorem. Okay, now for this left side, this is just the integral. What about the right side? To compute this right side, I need to compute what? The curl. So let's compute the curl. The curl is the determinant I, j, k, d by dx, d by dy, d by dz, what? f1, f2, and what? 0. Which is what? What is with I? It is 0. Why is it 0? I want to explain this. Why is it 0? Because what is with I? You cross the first, right? The first row, the first column. Then you say this minus this. But this is 0. The first one is 0. The second one is 0 because you are differentiating f2 with respect to z. And f2 does not have any z. Remember, the original function, is completely in terms of x and y. So this is why the first component is 0. The second component similarly is 0. What about the third component? So now what is with k? Okay, so now what is with k? I'm writing it again just to make everything very, very clear. Quickly. So what is with k? It is this minus this, right? Which is what? Which is what? Exactly. Which is df2 by dx minus df1 by dy. This is exactly what we see in Green's theorem. Okay, so this is the curl. This is the curl. Now after finding the curl, now I need to find what? I need to find a parameterization for the surface, because this is how we compute the surface integral, right? So now we find a parameterization for the surface. What is my surface again? It is something like this. It's a strange surface. It's like the desk, right? It is like the desk. I mean, we did an arbitrary curve that encloses some area. It could be anything. It could be a disk. It could be a rectangle. It could be arbitrary, anything. Okay, so now I need a parameterization for this surface. So what is R of uv? It is, we don't have an explicit relation, so it could be anything. It's arbitrary. So the x component is u, the y component is v, and the z component is 0. We are laying on the xy plane, but the u and v are free. So basically, the u plays the role of x, the v plays the role of y. So it's like saying x, y, 0. That's it. So we didn't do anything, basically. What about the normal vector? The normal vector is r sub u cross r sub v. What is that? This is I, j, k. R sub u is 1, 0, 0. R sub v is 0, 1, 0. And if you agree, this is 0, 0, 1. So what we've got is that the normal vector is 0, 0, 1. It's the upward normal vector. This is the n. So please, in applying Stokes theorem, we need to be very careful with the orientation. In applying Stokes theorem, if you imagine yourself this orange thing, so this is you. You are looking at the curve. What's the orientation? The clockwise orientation. Then you say, okay, I want the counterclockwise orientation. Fine. So this is how we decide our orientation in Stokes theorem. Okay, now you apply what? You apply Stokes. So what does Stokes say? So Stokes theorem now says that the curve integral of f dot dr in the orientation we just showed. We just said this is our orientation. We just said this is our normal vector 0, 0, 1. Okay, so the Stokes theorem says this curve integral is equal to the double integral of what? The function. What was the function? The function is just f. F dot it's curl f when we apply the divergence theorem. Curl f dot n dA, and here we just have the surface. Remember, this was our surface, which is parameterized by just uv and 0. So the integral c f dot dr. Now, what is the orientation? What is the orientation? It is, if you agree, this is exactly the orientation we want in Green's theorem. In Green's theorem, the orientation is so that when you move along the curve, the interior is to your left. So if you imagine someone moving here on this curve, so this is someone walking on the curve, this is the left. The left is the interior. So this integral is equal to what? It's equal to double integral u over u and v of what? You compute the curl, but we computed the curl. What was the curl? It is 0, 0, df2 by dx. This is in the previous slide, df1 by dy. Dot n, what was n? 0, 0, 1, du dv. So this is exactly double integral over x and y, because u and v, they are exactly x and y, and when you do the dot product, it's df2 dx minus df1 dy dx dy, which is dA. So basically in the left side you have this quantity, in the right side you have this quantity, but this is exactly what? This is exactly Green's theorem. So this is the relation between Stokes and Green's. Remember, we started, this line here is not Green's. This is Stokes theorem. But after doing the computations, with the previous computations, we reached Green's theorem. So basically, we can look at Green's theorem as a special case of Stokes theorem. That's why some people, sometimes, they call Green's theorem just Stokes theorem, because it follows from Stokes theorem in R2. That's it.